This is Calculus 3 video lecture number 18 on Lagrange multipliers. Now, in the previous section, we developed methods to find maximum and minimum values of functions of several variables. And in this section, we're going to develop another method which is useful whenever the values to be found are subject to additional requirements, which we call constraints. So our task is to find the maximum or minimum values of a function, f of xy, subject to some constraint equation, which is given by g of xy equals k. So what this means is the point that we find has to be on the curve g of xy equals k. So notice that curve is shown here. Okay, but of all the points on the curve, I want to find the one where f of xy is the largest or the smallest. I want the extreme values. So how would I go about that? Well, it's easier to visualize this method geometrically for functions of two variables. So here we see some level curves for f of xy equaling a constant c, and then here's our level curve g of xy equals k. Now visually, I think we can all find where f of xy achieves its maximum subject to the constraint, and that would happen right here at this point where f of xy is equal to 10. This is just some arbitrary example. Now notice here, it appears from the figure that this is when the curves just touch each other, meaning that they have a common tangent line. And if they have a common tangent line, that means that the normal lines at this point, let's call it x naught, y naught, those normal lines are going to be identical. Well, what does that mean? The gradient vectors, therefore, are going to be parallel. And if you need a little refresher on gradient vectors, then check out video lecture number 16. So what does that tell us? Well, that tells me that the gradient of f at x naught, y naught is parallel, or it's equal to some constant multiple, which we'll call lambda, times the gradient of g at x naught, y naught. So lambda is a scalar. And that basically is what you do to set up the process of finding extreme values subject to some constraint equation when you use the method of Lagrange multipliers. Now, if f is a function of 3 variables, then you would have level surfaces rather than level curves, but the idea is basically the same. You're just going to take the gradient of f and set it equal to lambda times the gradient of g, your constraint equation. Okay? So for the first example, we're actually going to revisit a problem that we worked on in the previous lesson in video lecture number 17. But now we're going to apply the method of Lagrange multipliers to solve it. So the example is as follows. Find the dimensions of the largest rectangular box in the first octant with 3 faces in the coordinate planes and 1 vertex in the plane 2x plus 3y plus 5z equals 90. And what is the maximum volume? Okay, so in this case, we want to maximize volume. And if you want to watch the video from the previous lesson, number 17, we showed that the volume could be computed by just taking x times y times z, since this rectangular box is in the first octant and the 3 faces are in the coordinate planes. So I want to maximize the volume. I'll call my volume function f of xyz, which is equal to x times y times z, and it needs to be subject to the constraint that one of the vertices lies on this plane. So it satisfies that equation. So subject to the constraint that 2x plus 3y plus 5z must equal 90. So that's basically my g of xyz. All right, so to begin the process, I need to take the gradient of f and set it equal to lambda times the gradient of g. So the gradient of f, if you'll recall, I'm going to take the partial derivative of xyz first with respect to x, so that would be yz. Then I take the partial derivative with respect to y, which would be xz. And then lastly, partial derivative with respect to z, which would be xy. And then I set this equal to lambda times gradient of g. So the partial derivatives are just going to be 2, 3, and 5. Beautiful. So now I have 4 unknowns to solve for, x, y, z, and lambda. So let's list out several equations. I can set the corresponding components equal to each other. So first equation I have is that y times z must equal 2 times lambda. Equating the second component, I would have xz is equal to 3 times lambda. And then third equation, we have xy equals 5 lambda. That's from this one. Okay, that's only 3 equations. I have 4 unknowns. The fourth one that I'm going to use is the constraint equation. So I know that 2x plus 3y plus 5z has to equal 90. Okay, well, there's quite a few ways to go about solving. One thing I could do is take equations 1, 2, 3 and isolate lambda and then substitute that in to the last equation. So equation 1, if I were to solve for lambda, I would get lambda is equal to yz divided by 2. And then that would also be equal to, working with the second equation, xz divided by 3. And similarly with the third equation, this would give me xy divided by 5. All right, now I'm just going to focus on these first two here. Yz divided by 2 is equal to xz divided by 3. Now here I can kind of take a little step that we typically do not allow when solving equations. And remember, we're trying to find the maximum volume, in which case I know I don't want x, y, or z to be 0. So I can actually cancel out z from both sides, because I know in this case I don't have to consider the option of z equaling 0. There's no way that would yield a max volume. Now, it's a big no-no to divide by a variable in math. We all know this. You should feel a little bit ill just watching me do that. I don't blame you. However, considering the context, this is fine because we're applying it to a case where we're after the maximum, and I know the maximum won't occur where z is 0. So just watch out. Don't take that step for granted, okay? And then this means that y is equal to 2/3 x. Okay, we'll save that here. And then I'm going to do the same process now for the next two equations here. So I have x, did I do it that way? You know what I did instead? No, excuse me. I'm going to set yz divided by 2 equal to xy divided by 5. So I can cancel out y again, actually. And then now I'm going to get that z is equal to 2/5 x. So I have z in terms of x, I have y in terms of x. I'm going to substitute this all into equation 4 now. And my z disappeared. Come back, z. Okay, here we go. So 2x plus 3 times y is 2/3 x plus 5 times z, which is 2/5 x, is equal to 90. And I have 2x plus 2x plus 2x. So what's that? That's 6x. So 6x is 90, which means x is 15. And then from up above, if x is 15, then y is going to be 10. And z is going to be 6. Okay? So there I know that those coordinates will yield the max volume. F of 15, 10, 6, x times y times z, and that max volume is going to be 900 units cubed. Okay. Now, if they just asked me to use the method of Lagrange multipliers to find all extrema, then I could not have eliminated the option of z equaling 0 and taken that for granted, but since I knew I only wanted maxima, I threw that away. Okay, so just be careful when you take liberties like that. All right. Let's look at another example. Which method would you say is easier, this one or the previous lessons methods? It's up to you. Okay, so find the dimensions of a closed cylindrical jar with volume 2,000 centimeters cubed that yields a minimum surface area. So when you're trying to figure out which function is f and which one's your constraint, f is going to be whatever you're trying to maximize or minimize. So notice here they say, all right, they want us to minimize surface area. Okay, so that's going to be my function f, the surface area function for a closed cylindrical jar. So it's got a lid and a bottom. Okay, so I want to minimize surface area. And I know surface area is a function of the radius and the height. So F is going to be a function of R and H. Now, I have a lid and a bottom. So the surface area for that is just going to be 2 pi r squared. And then if I unroll it, I have a rectangle here, right? Let's make it match. So this is going to be the height. This is the height. And I know that the length of the rectangle is 2 pi r because it comes from the circumference, right, of that circle. So the formula now for the surface area is going to be 2 pi r squared plus 2 pi r h. And that needs to be subject to the constraint that g of r and h has to have a volume, which is pi r squared h equal to 2000. Okay. Now, obviously you'll minimize surface area if you don't even make a cylinder, but that's not going to be relevant because we need to make sure it's going to hold a volume of 2000 centimeters cubed. So in this case, again, we know that we can exclude the cases if r and h were going to be equal to 0. All right, so let's get started. I have the gradient of f is equal to lambda times the gradient of g. And it's up to you. I wrote out r first and then h. You could do it the other way around, but just be consistent. That way your components can equate properly. Okay, so first I'm going to take the partial derivative with respect to r, since I wrote f as a function of r first. So then I would have 4 pi r plus 2 pi h. And then now I'm going to take the partial derivative with respect to h, which would just be 2 pi r. And then this is going to equal lambda times the gradient of g. The 2000 doesn't matter, right? If I subtracted it over and then took the gradient, took those partial derivatives, the derivative of 2000 is just going to be 0, so don't lose any sleep about it. Okay, so pi r squared h, if I take the partial derivative with respect to r, I'm going to get 2 pi r h. And then taking the partial derivative with respect to h, I'll just get pi r squared. All right, very nice. So now let's set up our system of equations here. So equation 1, I have that 4 pi r plus 2 pi h is equal to 2 pi r h times lambda. Equation 2, I have that 2 pi r is equal to pi r squared times lambda. And then equation 3, the last one's always your constraint equation. So pi r squared h is equal to 2000. Okay, so let's see. Let's just dive into equation 1. Can I clean up anything? I notice I can cancel out a 2 pi from all the terms, right? So I'm going to have equation 1 cleaned up is 2r plus h is equal to r h lambda. Okay, let's move on to equation 2. That wasn't too enlightening. Equation 2, I can divide out a pi, and I have 2r equals r squared lambda. Now remember, we mentioned earlier that r isn't going to equal 0, which means I can throw away the case of r equaling 0, so I'm just going to cancel it out on both sides. So 2 equals r times lambda, which means that lambda is equal to 2 divided by r. Okay, that's helpful because I can take that now and substitute lambda equals 2 over r into equation 1. So let's substitute that into equation 1. So now I have 2r plus h is equal to r times h times 2 over r. So notice now this r is going to cancel out. And then I have 2r plus h equals 2h, which means that h is equal to 2r. Great. So now I can put this into the constraint equation, equation 3, and I'm pretty much home free. So now into equation 3, I know that pi r squared times, remember h is 2r, is equal to 2,000. So that means r cubed is equal to 1,000 over pi. So r is equal to, take the cube root, 10 over the cube root of pi centimeters. And then since h is double that, right, h is 2r, then h is going to be 20 over the cube root of pi centimeters as well. All right, let's box that up. Voila. Very nice. Now, what if you have more than one constraint to worry about? What would you do in such a scenario? Well, in this situation, the solution has to lie on the intersection of both constraint curves, which means that the gradient of f lies in the plane that's determined by the gradient of g and the gradient of h, which means that I could write the gradient of f as a linear combination of the gradient of g and the gradient of h, and therefore I can write it as follows. So I just introduce a new scalar, so I would have gradient of f equals lambda times the gradient of g plus, and then we usually use mu next, times the gradient of h. Okay, so same process, you just have to take another gradient and slap a mu on there. Okay, so this example says, find the extreme values of f of x, y, z equals z minus x squared minus y squared, subject to, and then now we have two constraints. So to get going, let's call this one g of x, y, z, and then this one's going to be h, okay? And so when I set up my Lagrange multipliers, I'll have gradient of f is equal to lambda times the gradient of g plus mu times the gradient of h. All right? And then from here, let's go ahead and take our partial derivatives, get our gradients. So gradient of f is going to be, partial with respect to x is going to be negative 2x. Then we have negative 2y. Partial with respect to z is just 1. And then this is equal to lambda times, now gradient of g, ooh, I love it, just 1, 1, 1, plus mu times gradient of h. So partial with respect to x is going to be 2x. Partial with respect to y is 2y, and there's no z, so that component's just going to be 0. All right, now we're going to set up our system of equations. So remember, we set each of the components equal to each other. Just don't forget your lambda and your mu. So equation 1 is going to be negative 2x is equal to lambda times 1 plus 2x mu. Equation 2, now I'm going to come and set all of the second components equal to each other. So we have negative 2y is equal to lambda times 1 plus 2y times mu. All right, equation 3 is going to be 1 equals lambda times 1 plus mu times 0. Ooh, so we just get lambda equals 1 already. Very nice. And then equation 4 is going to be constraint equation g, so x plus y plus z is 1. And then equation 5 is going to be x squared plus y squared equals 4, our other constraint equation. And then check. We have 5 unknowns, right? X, y, z, mu, and lambda. And we have 5 equations here. So we can solve the system. So how to begin? Well, I noticed if I play around with equations 1 and 2 and subtract them, I can get somewhere a little interesting. So if I take equation 1, subtract equation 2, I'm going to have negative 2x plus 2y. Now the lambdas are going to cancel out, and then I have 2x mu minus 2y mu. And then I notice I can divide everything out by 2, so I'll have negative x plus y is equal to, and then why don't I just factor out that mu also while I'm at it on the right hand side, so mu times x minus y. All right, now if I were to divide by x minus y, that would only be allowed as long as x minus y wasn't 0. And I don't know if that's the case or not. So what I'm going to do is consider two cases. Case one is going to be x minus y equals 0. If x minus y is equal to 0, that means x is equal to y, right? And then case 2, which I'll consider after, is if x minus y does not equal 0. All right, so we're in the world of case 1. I'm assuming x is equal to y. What can I do with that? Well, I notice over here equation 5 only includes x's and y's, so that looks like a nice place to go. So into equation 5, I'll have x squared plus, I'm assuming x is equal to y, right, in this case, so x squared plus x squared equals 4, which means 2x squared is 4, so x equals plus or minus the square root of 2. Well, that's good. Now I can go to equation 4, and since, remember, we're assuming x is equal to y, then if x is rad 2, y will also be rad 2, plus z is equal to 1, which means z equals 1 minus 2 rad 2. Or, other possibility, remember, was for x to equal negative rad 2. So in that case, if x is negative rad 2, then y is also negative rad 2, plus z equals 1. So now z would equal 1 plus 2 rad 2. Okay, so those are two possibilities. What I'm going to have to do is evaluate the function at each of those ordered triples in order to determine if I have an absolute max or min in order to compare them, okay? So I'll save these for later. This is all of my options from case 1. I've exhausted case 1. So I have f of rad 2, 1 minus 2 rad 2 to evaluate. And then I also need to evaluate f of negative rad 2, negative rad 2, and then 1 plus 2 rad 2. Okay, good. Now we're going to move on to case 2 and see if we get any additional options there for extrema. So now I'm assuming that x minus y is not equal to 0. Well, remember we were here, and if x minus y is not equal to 0, then that means we can divide by it, right? So I would have mu is equal to negative x plus y, that's the same as y minus x, over x minus y. And y minus x over x minus y, that equals negative 1. Ooh, okay, so I got mu equals negative 1. Now let me substitute that into equation 1. And then I would have negative 2x is equal to, now don't forget, we already know that lambda is 1. So let's just substitute that in. 1 plus 2x times mu, which we have is negative 1. Well, now notice I have negative 2x is equal to 1 minus 2x. Well, that's impossible, right? 0 does not equal 1. So that means I have a contradiction. This case is not valid because the assumption I made in this case is not valid. What was that assumption? That x minus y was not equal to 0. That assumption is false. So that means the only assumption that works, or that is valid, is that x is equal to y, which was from case 1. And I already have all of the possible extrema listed below. So now I'm just going to evaluate them in the function. And remember, where was f of x, y, z? All the way up at the top, hiding from us. So here's f of x, y, z, which is z minus x squared minus y squared. Okay, so now I'm going to substitute these values in to see what we get. So this is going to equal z, which is 1 minus 2 rad 2, minus x squared, which is 2, minus y squared, which is 2. So this is going to be negative 3 minus 2 rad 2. And then the other option, I'll have z, which is 1 plus 2 rad 2. Again, minus 2 minus 2. So in this case, I'm going to get negative 3 plus 2 rad 2. Okay, so it's pretty clear to see this value here with positive 2 rad 2 is going to be my absolute max, and the other one is going to be the absolute min. All right. Now, there can be several methods or approaches to playing around with the system of equations in order to find the absolute max and min. This is not necessarily the only way, but just make sure that you're organized with your work and you follow a logical process that's valid. That way you don't miss any possible solutions, okay, or possible extrema. All right, let's just look at one last example here, again with two constraints just to spice it up, you know. So find the extreme values of f of x, y, z equals 20 plus 2x plus 2y plus z squared, subject to the two constraint equations here. So again, let's just call this g, and we'll call this one h. And remember, we have the gradient of f equals lambda times the gradient of g plus mu times the gradient of h. So let's go ahead, let's get that gradient of f. So taking our partial derivatives, partial with respect to x is 2, partial with respect to y is 2, and then 2z for the last component. And this equals lambda times gradient of g is just going to be 2x, 2y, 2z plus mu times, and then gradient of h is just 1, 1, 1. All right, again, I have 5 unknowns, so I should have 5 equations. So first equation, we're going to set all of the first components equal to each other. So we have 2 equals 2x times lambda plus mu. Equation 2, I have 2 equals 2y times lambda plus mu. Equation 3 is going to be 2z equals 2z lambda plus mu. What happened to mu? Come back. Okay. Equation 4 is going to be constraint equation g. So x squared plus y squared plus z squared is 11. And then equation 5 is going to be x plus y plus z is 3. All right, so let's see here. Maybe we'll take equation 1 and 2 and subtract them again, like before. And I'm picking that because the mu will cancel out, and then also the 2's on the other side will cancel out. So I feel like I can kind of play around with that pair of equations more easily than a different pair. So I'll take equation 1, subtract equation 2, and now I'm going to have 0 is equal to 2x times lambda minus 2y lambda. All right, so I can factor out a lambda and a 2 here. So 2 lambda times x minus y. So now here I can apply the zero product property from way back in your algebra days. And basically I either have 2 lambda is 0 or x minus y is 0. So we can call those two cases if you want. That's basically what we've been doing. So case 1 is going to be where lambda is 0. And then case 2 is going to be if x minus y is 0. Okay, so if lambda equals 0, looking at our 5 equations, what's the best place to go from there? Well, how about equation 2? Because if I go to equation 2 and I know lambda is 0, then I know 2 is equal to mu. Ooh. And then from there I can go to equation 3. Since lambda is 0, I would have 2z is equal to 0 plus mu, which is 2, which means z is equal to 1. This is shaping up nicely. Okay, so z is 1. Where to go now? How about equation 5? Because I have z. So in equation 5, stay away from that quadratic one for now. So equation 5, I have x plus y plus, but I know z is 1, is equal to 3. So I can solve for y. Y is equal to 2 minus x. Now, why did I want to do that? Because it's time to go to equation 4 with all this info. So into equation 4 we go. We're going to have x squared plus y squared. Remember, y is 2 minus x. Plus z squared, which is 1, is 11. Now I'm going to multiply this all out. So we have x squared plus 4 minus 4x plus x squared plus 1 is 11. So I have 2x squared minus 4x. 4 plus 1 is 5, minus 11, that's negative 6, is 0. Dividing the equation by 2, I have x squared minus 2x minus 3 is 0. And this factors, so I get x minus 3 times x plus 1 is 0, which means x is equal to 3 or negative 1. Okay, so let's see here. I have to evaluate f of 3, and if x is 3, then remember y is 2 minus x. So that would make y equal to 2 minus 3, negative 1, and we already had that z was 1, right? So that's one option from this case. The other one is if x is negative 1. So if x is negative 1, then y is going to be now 2 minus negative 1, so positive 3, and then z is 1. So we'll evaluate those in just a minute. Okay, I've exhausted all of the options for case 1 where lambda is 0. Now let's consider the other option for the zero product property if the other factor of x minus y was equal to 0. Well, if x minus y is equal to 0, that means that x is equal to y, right? And hey, let's go back to equation 5 now. If I know x is equal to y, equation 5 tells me that x plus z is 3. So that means z equals 3 minus 2x. Where to go now? Back to equation 4, just like last time. So let's go to equation 4 with this. So I have x squared plus, remember, x is equal to y, so I'll have another x squared plus z is 3 minus 2x squared equals 11. And then multiply this all out, so you have x squared plus 9 minus 12x plus 4x squared is 11. And then let's combine our like terms, so we have 6x squared minus 12x, and then 9 minus 11, negative 2 is 0. Dividing by 2, we have 3x squared minus 6x minus 1 is 0. And dun, 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 this does not factor, so it's time to bust out the quadratic formula. Did you forget it? Has it been so long? I hope not. I have a video actually on the quadratic formula if you need a refresher. Okay, so x is going to be positive 6 plus or minus square root 36 minus 4 times 3 times negative 1 all over 6. So that's going to be 6 plus or minus, now let's see here, that's going to be 36 plus 12, which is 48. 48 is 16 times 3, so that's going to simplify into 4 rad 3 over 6. And then that reduces to 3 plus or minus 2 rad 3 over 3. So that's what x is going to be. X is equal to y, so don't stress about that. And then the only difference now is I have to find z. So z is going to equal 3 minus, remember I have that from up here. Here's z, 3 minus 2x, okay? So 3 minus 2 times 3 plus or minus 2 rad 3 over 3. Well, if I get a common denominator, that's going to be 9 over 3, right? So then I'm just going to end up with 9 minus 6, and then plus or minus 4 rad 3. But you're going to have the opposite sign there. So this is going to be a positive 3 for 9 minus 6. And then I'm going to put minus plus 4 rad 3 over 3. Okay, good. Did you get lost? 9/3 minus, this is going to be 6 minus plus 4 rad 3 over 3. Okay, hopefully you can do that all in your head. Okay, so I have 2 more points to evaluate the function at. Let's list them out. Here we go. So I have f of, now since x is equal to y, I'll have 3 plus or minus 2 rad 3 over 3. 3 plus or minus 2 rad 3 over 3. And then remember, z had the opposite sign. So 3 minus plus 4 rad 3 over 3. All right, so don't worry, I did this already. This comes out to 91/3. All right, the other two, f of 3, -1, 1 is 25. F of -1, 3, 1 is also 25. So what could I say? Well, I know 25 is less than 91/3, right? 25 is 75/3. So these two are where the absolute min occurs, and the absolute min value is 25. And then here at these 2 points, we have the absolute max, and the absolute max value is 91/3. This problem was not for the faint of heart, huh? So good. Just tested everything you've ever done. So that's it. We don't need to do that last example lurking down below. We'll just end on a high like this, and that concludes the lesson on Lagrange multipliers.